ICML 2021. We are now our keynote session of the day, and we have a wonderful program. So let me introduce our keynote speaker, Esther Duflo. Esther Duflo is the Abdul Latif Jamil Professor of Poverty Alleviation and Development Economics in the Department of Economics at MIT. And she's also co-founder and co-director of this lab. On a sabbatical this year, she's holding a position professor at the School of Economics in Paris. So we have the pleasure to have her this year in Paris. And in her research, she seeks to understand the economic lives of the poor with the aim to help design and evaluate social policies. She has worked on many topics close to economics, of course, on health, education, financial inclusion, environment, governance, and more recently even on COVID vaccine. And certainly you know her because she has received numerous academic honors and prizes, including the famous Nobel Prize in Economics Science in 2019. With co-laureates Abhijit Banerjee and Michael Kramer. And now we have the pleasure to enjoy her talk, and I give her the floor to her.
Hello, I'm very happy to present today a talk called Plumbers and Mechanics, How Machine Learning Can Complement Randomized Control Trials in Policy Experiments. I must say, in every single talk, every single opportunity, I always have a little bit of an imposter syndrome. I always wonder why I was invited to give this particular talk, whether I am really the right person to do it. And in this talk, perhaps more than in others, because I really I'm not an expert in machine learning. I'm a consumer of it. I have written several papers along with machine learning colleagues using and developing tools to use in randomized control trials, but you guys are really the experts. What I am is a practitioner of randomized control trials in the field. In other words, what I do is I run policy experiments to try to understand what works and what does not in fighting poverty. For example, how to convince parents to vaccinate their children, how to make sure kids learn in school. Those are causal questions for which there are often many competing ideas. For example, to vaccinate children, you could say that it's very important to have a clinic very close by, or you could say that people should be given incentives, or you could say that they should be forced to do it, or so on and so forth. And usually there is no useful guidance from theory. We need experiments to find out. We need to try out and rigorously test the ideas that come up. I have argued in several pieces of work that economists must be willing to engage with the messiness of the real world. I have called them, in a way, plumber. Try things out in the real world, get it wrong, tinker, experiment, try again. This is what a plumber do in real life, and this is, in many respects, what policymakers should be doing, and what economists can also help doing. And randomized control trials are excellent tools for plumbers because they force you to try something out, find out whether it works, and if it doesn't, try something else. Now, if I call economists plumbers, then you might wonder how I want to call machine learning experts, that is, you guys. And naturally, you might think of them as mechanics. Mechanics is the word that seems to be the most appropriate for machine learners. Why? Well, you are trying to make machines learn, so you seem to be working with machines. They are not anymore made of nuts and bolts. They are more computer machines, but they are machines. And you are tuning their procedures, often quite empirically, often without much theoretical guidance, often ahead maybe of the theory. Very much like a mechanic is trying to understand how their machine works. Empirical economists, of which I am one, tend to take these engines for granted and have no idea what's in it. So the plumber has to trust that the mechanics knew their statistics when they built the machines. Now, why do plumbers would need to work with mechanics? At first blush, machine learning and randomized control trial would seem to be very different tools to be used in very different circumstances. You would use machine learning for prediction, randomized control trials for causal inference in very low dimensional settings, so typically one parameter in what is the effect of X on Y. There is very policy relevant use of machine learning in a prediction role in development economics. For example, there is recent work by Josh Blumenstock and others on using cell phone metadata as well as satellite imagery to very quickly target poor people for a cash transfer during COVID-19 in Togo. So what they did is that the government was looking for a way to deploy very rapidly a cash transfer, but to try to target it to some people. And what the government was using is very, very, very imperfect data. They didn't have the time to collect better data on people's consumption, on people's assets, and do a registry of who might be poor. And what they did is to combine data from the phone record, which is plentiful, as well as satellite data, all of which is readily available, to make a prediction that someone might be poor. And in their study, they compare it to what you would get if you were able to do a much more detailed consumption survey, which is, of course, not something you can do in this case. What they find is that these new tools, machine learning tools, work much better than the approach that the government would otherwise have used with very poor administrative data, but less well than if you were able to collect all of the data possible on people's actual poverty level. But that was not available at this time. So that's an example of using machine learning in some sense to its traditional use of prediction to a very good effect in development work. But it is not the only use of machine learning tools. First of all, there is a use of machine learning tools for causal inference. And that's the first place where mechanics and plumbers to talk to each other, because randomized control trials would seem to be a useful benchmark to compare the performance of machine learning tools to a proper estimate of causal effect from an experiment. The second aspect, the second place where you might find a useful collaboration between machine learning tools and randomized control trials is in the practice of the experimenters themselves. There are many kinds of experiments. Sometimes experiments are inspired by a specific theory. They follow a precise experimental protocol that derive from that model. And in that case, there is no need for machine learning. You might specify one set of regression to run and just go ahead and run them. So that's kind of the typical framework for clinical trials, for example, for a vaccine, where there is precisely one treatment to be estimated precisely in one population. And then you just run your experiment, compare the means, and you're essentially done. There is no place for machine learning. But plumbers also engage in what I would call policy experiments. Those are experiments often done on a much larger scale, which are designed to provide guidance for policymakers for what policy to do and where to do it. And those are settings where we don't have an oracle. We don't have a best foot forward. We don't know in advance what treatment is the best that we want to test, for whom, on what outcomes. And these types of experiments are the ones where machine learning tools will become particularly useful. In this talk, I'm going to discuss the two aspects: when RCT can serve as benchmark for machine learning estimated causal impacts, and the second is how to use machine learning tool for STs. I've worked on both of these aspects, so I briefly want to talk about both. So first, starting using RCT as a benchmark for evaluating the performance of machine learning tools. So the inference question, or the causal impact question, is how the predicted value of variable y change if we increase a regressor d by a unit, holding other regressor z fixed. We can answer these questions within the context of a partially linear model, which reads y equal beta d plus gz plus epsilon. And y is the outcome variable. D is what we care about. This is low dimensional, typically one treatment. And z, on the other end, is a high dimensional vector of other regressor features, which we in economics often call controls, that we really don't care about. The coefficient beta is what we are interested in. It's the answer to the inference question. There are many modern methods to estimate this parameter, and with Viktor Chernozhukov and many others, we propose to use a double machine learning. So what it does is that it works in 3 steps. In the first step, you take an auxiliary sample. You prefer a machine learning tool, forest, deep networks, anything really, whatever you prefer, to build estimators lambda z and mz of the best predictor of LZ and MZ. Then, using your main sample, you obtain the estimates of the residualized quantity. Y hat is Yi minus L of Zi, the best predictor for Y given Z, and D hat is Di minus M of Mz, the best predictor of Z. So in a sense, what we have done is apply the Frisch-Vaux theorem, which is that we can partialize. Once you've done that, then you're basically home free. You obtain the estimates of beta, which you can name beta 1. Beta 1 is just the results of running a standard linear regression, ordinary least squares, to obtain your first estimate of beta. Then you reverse the roles of the auxiliary and the main sample. You repeat your first step. You obtain another estimate of beta, which you denote beta 2. And then you take the average of the 2 estimates from step 1 and 2 to obtain your final estimates. So basically, this is exploiting, combining the long tradition of economics that we can partial out whatever we don't care about, both from the outcome variable and from the regressor. And then we can run a standard regression on the partialized things. So this actually, in theory, works very well, and in simulation works very well as well. But there is no magic here. This is just a disciplined way to use a large number of covariates without making much of an assumption of their how they might interact with each other, the functional form, what might matter, etc. So this is really just exploiting the existing knowledge for a setup where we might have many more variables. But of course, in that case, the causal estimate is only as good as the covariates. And in the real world, it could be that even if you have many covariates, you just don't have the one that ensures that once you've controlled for them appropriately, you in fact have a proper causal estimate of the effect of your regressor on your outcome. It could be that there is still omitted variables that are very important that are just not in the data set. It's not because we have many variables that we have all the one that matters, and it's not because we combine them in sophisticated, complicated ways that we have solved all the problems. So to assess the potential of these methods with potentially large amount of control variables, simulation don't work. You need to compare to a setup that is close to the truth in the real world. Unfortunately, we don't have that, otherwise we would need to estimate the problems. So when can we have that? Well, we can have that when we compare the estimates provided by machine learning with estimates that come from a randomized control trials, because we trust in the causal estimates that derive from a randomized control trial. So we have a paper with Michael Kramer and Pascaline Dupin, where we are doing just that in Ghana. This is a longitudinal study that we started in 2008. At that time in 2008, we sampled 2,000 students. Notice the sample size, it's not enormous, who had been admitted to local secondary school but had not enrolled because they didn't have money. We found them, we randomly selected half of them, and we gave them a 4-year scholarship to attend local secondary school. And then since then, we've been following them up every year to find out what was happening to them and to survey them until 2019 and even 2020. What we are doing in this paper is what, as economists anyway, we would call the Lalonde exercise, after Bob Lalonde, who is the first one to say, let's use the benchmark of randomized controlled trials to compare any other observational methods. So here what we do is that we first take the control group, and we used our methods developed in Chernozhukov et al. To estimate in the control group the following regression, which has D as the effect of secondary education, a bunch of control variables that we treat as nuisance parameter. And we are going to compare that with our best estimate of the causal parameter, which is an instrumental variable estimate, where going to secondary school is instrumented by T, the treatment, which is someone received a scholarship. We're also going to compare that with a naive OLS controlling for some obvious control variables. Now, there is a caveat, which is it's an IV estimate, and therefore we don't estimate the returns for the overall population or for the average person, but for the compliers, which is the average person that was prompted by our experiment to go to school. Some of the control students who didn't get a scholarship went to school anyway. Some of the treatment students who got the scholarship did not go to school anyways. So only thing we estimate with the IV is this weighted inference. What is the solution? Well, we are going to use machine learning to estimate treatment effect heterogeneity in the first stage, in the way that I'll explain a little bit later. And then we are going to estimate a weighted regression so that the resulting estimate represents the effect for people who are, in terms of the observable, very much like the complier. So the true comparison will be the weighted double machine learning versus the IV. What do we find in this case? If we look at, for example, a knowledge score, which in a survey that we administered 5 years after the initial randomization in 2013, we're finding that when we compare OLS, the naive OLS without any control to the IV, the naive OLS overestimates the impact of education. So the impact of education is found to increase the total standardized test scores by 0.26 standard deviation for people who go to school. And we see that it's too large compared to the IV, which is 0.15. That makes a lot of sense because the people who go to school are already people who were better to start with in terms of their knowledge or their cognitive capacity. So this is upward biased. Now, how well does regular control do? Almost nothing at all. How well does weighted double machine learning do? It improves things. It gets closer to the truth, but it doesn't get quite to the IV. Second example, number of children ever had. There we are doing a little bit better. So the impact of going to school on having kids on female is negative. So women are less likely to have kids early, to have many kids early, which is a positive in this population. The effect is more negative in the OLS than in the IV, so it's overestimated. And the weighted DML is now very, very close to the IV, if anything, a little bit smaller. So here the weighted DML got very close to the truth. So far so good. We're getting better. We're getting towards the causal effects. But on the other hand, if we are now looking at the wage effect, for example, we're finding results that are much less satisfactory. For example, if you look at earnings in the last 6 months, the OLS severely overestimate the impact of getting a scholarship on earnings compared to the IV, which is essentially zero. And the weighted double machine learning doesn't get us anywhere close to the IV estimates. So in other words, for many outcomes, DML seem to come closer or quite close to the IV estimates, but for some it's still very different. And at this time, we don't have a theory for why it would work for some outcomes, why all of the observable variables that we have taken together are good to soak up the unobserved variability between those who go to school and those who don't go to school when we look at test scores, when we look at fertility, but why it does nothing for earnings. So machine learning is not a miracle, and we need to keep that in mind, and we need to continue, in a sense, refining, using the machine learning methods, comparing whenever possible to causal estimate coming from RCTs, in order to try to form a better sense of what we're able to pick up with a very large number of observable variables, what we may not be able to pick up. What matters is also to remember that as machine learning experts, you need to remain somewhat humble in the sense that We shouldn't get enamored enough of the technology to think, well, it's fine, we can develop the tools to get at causal estimate no matter the situation. The estimate is only going to be as good as the data, and in particular, it's only going to be as good as the data we have to capture and observe heterogeneity. For the rest of the talk, I'm now going to talk about how I have collaborated with econometricians and statisticians to look at the, to use and to develop tools to have a more creative and more useful role for randomized controlled trials. And I'm going to do that in the context of one particular example, which is a very important policy example, which is how to convince parents to immunize their kids in India. Immunization, of course, is the talk of the town. Everybody talks about how to get people immunized. But it's been an issue for childhood immunization for many years. The rate of childhood immunization has improved in the world, but still every year, something like 25 million children go without the essential immunization. So in this project, we worked with the government, who was interested to see how to encourage demand for childhood immunization with affordable measures. The context is one where only 40% of children get fully immunized in Haryana, that is, they receive the 5 vaccines in the extended program of immunization. There is a very good supply network for immunization with immunization camps, etc., but very large gaps in demand. The objective was to experiment to figure out how to boost demand and how to scale up what works in the experiment later for the government. So the government really wanted to do something that was on a sufficiently large scale that any problems would emerge in the course of the experiment itself, and also that would give actionable results that they could then embody into policy. Now, what did we know when we started? Well, there have been many smaller experiments, proof of concept experiments, that shows us several things. First of all, incentives matter. So the idea of providing beers for getting immunized for COVID is not new. The idea of providing small incentive to parents has been tested many times, and it is effective. Using the social network. So again, this is something that very much was done in the COVID-19 immunization in the US with resorting on community leaders, etc. So the idea here is to use people from the community as immunization ambassadors, and in particular to select people who are particularly central in the social networks and therefore can talk to a lot of people who will themselves talk to a lot of people and therefore spread the news on immunization. And finally, SMS reminders for immunization. This project was run on a large scale, 7 districts, 2,000 villages, with only 9,000 with full baseline and all the interventions conducted, so I'm going to use mostly this 900. 300,000 kids were involved and 74 were fully immunized. And despite what was known about what might work to encourage immunization, a lot was not known. For example, we didn't know whether immunization should be, the incentives should be high or it should be low. We didn't know whether it should be increasing with immunization. We didn't know who the best ambassadors would be. We had no idea how this intervention would interact with each other. Would they be complement or would they be substitute? Would they detract from each other or would they work together? All of that was not known and could really not be known without trying. So what we did is that we ran several treatments, all cross-cut. First, we introduced tablets to help nurses carry out their immunization and record data and test the data and collect the data. We're working at tests. We try 4 variants of small incentives. Targeted SMS reminders to parents with 2 levels of intensity of coverage of the village, mobilizing social network in villages, and 4 ways of selecting the seats. And we're working at scale. The incentive and the reminder intervention covered 2,400 villages, and the social network intervention 900. So this is to give you an idea of the experimental design. And because everything is randomized, all of these cells cross-cut to each other. So at the end of the day, we have many cells. we have about 75 different possible treatments. This gives you an idea of how we had to set up our own data collection service. So a group from MIT developed an application from us, which was hosted on a server that we run. When an A&M vaccinated a child, she indicated the information. Then she this information got stored on the cloud, which generated reports and allowed us to give people both their mobile recharger for kids who were immunized and in the right villages, and also the schedule for SMS reminders. So I'm putting these slides up to tell you that in many cases, for people who work in the real world, in particular in development economics, the data doesn't exist. You don't acquire it. You have to make it. In this case, we were able to make it on a large scale, and we have a large data set. We also have to do a lot of work to check the quality of the data, because after all, it all depends on what is entered by the nurse on the tablet. And you might think that they might cheat or they might make mistakes, etc. So on top of that system, we had a separate back-checking system. We back-checked several thousand kids. 93% could be found and surveyed, and the quality was generally very good. So that gives us, in this case, confidence that we can work with the administrative data, which is good because that gives us a large data set to work from. Now there is a bunch of stuff, as I was saying, that we don't know. Where all of these variants, do they matter? How does it interact? No guide from theory on any of this. Where will the program work? There could be huge heterogeneity. There could even be backfiring in some places where people are already getting immunized, or where people are somehow against the government and don't like the idea of incentives and reminders. So just these two pieces of information, what will work best in this different set of things? And the heterogeneity leaves many, many, many degrees of freedom. So our experimental design has 75 cells for 900 villages. Some people work with adaptive treatments. It would not be possible in our setting because we only have one government their attention is available for only a small amount of time. So we have to run this one experiment and just run it. We cannot keep evolving it. And we have 36 baseline variables to potentially control for and look for heterogeneity. Once you interact them, that's also a lot of possible differences to look for. In addition, there are many other questions here one might ask, which I'm not going to ask today. Whether there would be a better design than throw everything at once, whether there is a best way to control for any baseline differences between the villages. So this is more similar to what I first did. What is the best program for each type of villages? That's the idea of personalized treatment. Here also we focus on one outcome, which is whether or not kids got the last immunization in the schedule. But in many cases, there are many outcomes in randomized controlled trials. So how do you adjust multiple hypotheses when there are so many that the usual adjustment would just mean zero power and finite sample size? That's another question people would be interested in. Those are the ones that I'm not going to do today, but I hope you keep in your mind that maybe you can work on for later. Now, here is a tension. The problem with all that richness is that there are too many possible tables for one reader, especially a policy reader. So the policy reader will want one bottom line, and when you select this bottom line, out of your 75 treatment, what will you show them? There is a worry that you might cherry pick either out of malevolence or just unconscious tinkering, running too many regression, check what you prefer, which would throw classical statistics out of the window and make the whole experiment not work. So one solution in the field of randomized controlled trial, which comes from the way they do things in medicine and is increasingly popular in psychology, for example, has been to tie the researchers' hands and simplify the design. So basically avoid this kind of design with 75 cells. You have only one treatment, one control. I've published in medical journal, and it is very difficult for them to deal with interaction. They much prefer one treatment. Force people to write a pre-analysis statistical plan. You specify all the outcomes that are primary or secondary, if possible very few, all the subgroups that you're going to look at. And of course, the treatment of inference penalizes any attempt to do more than one thing, because if you do more than one thing, you have to adjust your p-values to take into account the fact you're running more than one regression. And very quickly, that becomes impossible, so you just focus on one outcome, one treatment, one group. Now, there is an issue with this approach because there is so much data that could be used, or either could be produced, or in our case was available, and it seems it should be used. More creative experimental designs could lead to more and faster knowledge accumulation. I'm giving you the example for Ariana, where we have 75 treatment options. We do not know what works best. If we had to choose one treatment or two, that would precisely be assuming the knowledge that we do not have. We would basically pretend that we are the oracle and we can prune many of the 76 out of the 77 version of the treatment. And that's not right, because I don't have that information. So in a sense, what's the point of running this experiment if I'm assuming 90% of the knowledge already? Why don't I just go all the way to the end and assume that it's known? I want to give you another example which is very relevant, which is the example of the development of the COVID-19 vaccine. So when Pfizer ran and Moderna ran their first trials, they had large samples, exactly one regimen. And this is what was submitted to the FDA, and the medicine was approved based on those. But it's a bit unfortunate in a sense, because given a hurry, you would think that we should have been testing more than one specific regimen, potentially many at the same time. At the same time, there was not an infinite number of people that could participate in the trial. And so you could not necessarily have an infinite number of people each in a cell. But there was certainly some value, for example, in varying how many doses you need and what is the intensity of how much vaccine do you need to put in each and all that. And if we knew that, then we might have, for example, discovered that using we're using half the quantity of the medicine is sufficient. Then we would be in a very different situation today in terms of vaccinating the world. So we haven't done that. Partly because we don't have the institutions. This is not really what the FDA is used to look at, partly because we don't have the tools yet. So that's a reason why it's kind of unfortunate to move. It would be unfortunate to move entirely in a direction where we are making the randomized control trial very, very disciplined, very, very simple, and this is what it is. Because then it would really slow down the accumulation of knowledge compared to the best we can do. But in practice, even though in principle the data exists, so when you have 77 treatments and a lot of subgroups, someone who is skeptical can run your regression, nobody has the time to do that. So it would be good to have a process to sort through this wealth of information for policy advice, so that we have a process, an algorithm, that the reader can trust to make sure that the process is fair and not manipulated. And this is really where machine learning can be extremely helpful, because machine learning can give us the tool to do this exercise of sort of sifting through the data in a principled way that doesn't give much freedom in principle. I'm saying in principle because in practice, having done it, I realize there is a lot of tinkering. But in principle, that gives a lot of rules and steps that you can follow. So you don't give up on the richness of the data that you have, but you have a discipline into how you look at it. So the idea, in a sense, is to specify an algorithm to find the right cut of the data, not to find a specific cut. And this is really an agenda that I've become extremely excited about. And I've started to, for very, very applied practical reason, in my practice and also for policy implications. So for the immunization application that I described, we've done it for two things. One is when we have many, many treatments, so choose which treatment works and what's the best treatment. We have a second paper that looks at heterogeneity in treatment effect with Viktor Chernozukov and others. And then Devavrat Shah has another paper using the same data. By the way, I'm very happy to share the data as I did with him. That looks at personalized treatment in a way, which is a combination of the two, which is which combination of treatment would work best for whom. I'm going to today to talk very briefly about the first two. So what happens when you have multiple treatments? So what we do is that we say, well, you have this 75, but really, probably you can eliminate a lot of them, and you can collapse a lot of them in a similar bunch to say, so for example, we have different versions of incentives. Maybe they're all the same. Maybe small and large incentive are all the same. And therefore, maybe small and large incentive interacted with SMS are also all the same. So we can collapse dosages that have no differences in effect that work the same. And we can eliminate policies that simply don't work. To do that, so we first do that. We represent the problem in a way that's amenable to pooling and pruning. We're doing that by, in a sense, parameterizing. It's just a manipulation of matrices to reparameterize the treatment in the form of treatment profiles where we use our extensive knowledge of what might pull together and what might not pull together to put them in the same bucket. It's theoretically very simple. So, for example, if you had only two treatments with each two variety, it would be very simple. In practice, it's when you have many treatments with many dosages, it becomes a bit complicated. We explain how to do it. Once you've done that, we implement lasso. We have to do some preconditioning of the data, which we do using a work by Rohi and Gia and Rohi, because this very way of representing the data in the form that's amenable to pooling and pruning leads the data to have a lot of correlations, because we have, for example, one variable that is any incentive, and then any incentive with a high level of incentive. Those two are by construction very correlated. So that creates too much correlation for naive lasso, so we need to do buffer preconditioning, but it works very nicely in this case. And then we run the post lasso once the variable have been pruned and pulled. We run post lasso for consistent estimate of policy effects. And we're still left with one last problem, which is there might be several variables that are still competing with each other. And by definition, in any small sample, the best policy will look too good because it will be subject to the winner's curse. By definition, it was selected as the best, so it is too good. So we estimate the best policy adjusting for winner's curse. The core idea of smart pooling and pruning is that in practice, most policies don't work. And the best is to detect a few that do and prune the rest. So we pull together the policies where dosage make no difference. That aids power. We estimate we deal with the irrepresentability with buffering, and then we can estimate the effect. So what do we find? First of all, in terms of the policy effect on the number of immunization, you can see that almost everything is eliminated. We're left with 4, which the average level of immunization is about 8 immunization per month. The immunization, the policy that works the best happens to be the one that combines everything: incentives, social network intervention, and the SMS, which increase immunization by 4 out of 8, so an increase of about 50%. And then there are another few policies that are also estimated, that are also effective. When we look at immunization per dollar, which is what is the effect, do we get per dollar spent, what's the effect on, or what's the best policy? Their incentive doesn't become that good anymore, because of course when you pay for incentives, you're paying a lot of people who would have been immunized anyways. So that doesn't become so cost effective anymore. And in fact, the most and the only cost-effective policy, the one that increased the number of immunization per dollar, is the one that combines social network experiment and SMS. So this is much cheaper and therefore also much more cost-effective. Then we adjust this data for the winner's cost. In the case of the effectiveness of the policy, the most cost-effectiveness policy doesn't change anything because there was only one policy selected anyways. In the case of the measles shot, you can see that the naive estimate, it's a little bit too high. It was 4 and now it's 3.26, but it's still an estimate which is advantageous compared to the status quo. So to summarize, what have we learned? Well, first we've learned that the standard tools of incentives and SMS may not be effective at large scale. Incentives are effective but not very cost effective. However, there is a huge value in leveraging social networks to diffuse information. We're also learning from a more methodological perspective the subtlety in dealing with numerous treatment bundle options. One might be willing to pare down, but it's only sensible when policymakers is already somewhat sure what works, which is really usually not the case. So with genuine uncertainty, you cannot assume you know the answer. In our setting, if you didn't have any interaction, you would have said nothing works. Well, in fact, the combination is what works. So smart pooling and pruning is a simple data-driven approach which helps guiding this process. Now let me give you a second example, which is of using machine learning to do more from an experiment, same experiment, which is the question of heterogeneity in treatment effects. So here we have the most effective, the policy that increase immunization the most is the combination of doing everything, but it is not cost effective. Now government can ask, well, it's not cost effective on average, but maybe there are some places where it tends to work much better, and maybe in those places it is also cost effective. So in other words, what the government wants to know now is what is the effect of the policy conditional on a set of covariates which I observe. So ideally, we would like to know the conditional average treatment effect, or CAT, which is the effect, the difference in the potential outcomes for any combination of observable variable Z. And we are in a setting where the treatment itself, D, is randomly assigned. Now, can you know that? Well, it's going to be very difficult. You could try and use machine learning methods to estimate this CAT, this conditional average treatment effect as a function of Z. But this is fundamentally extremely difficult, and any of you who work with causal machine learning will know that it's fundamentally difficult to obtain consistency and even harder to obtain credible inference using machine learning. These are results which are quite old. Consistency can be achieved if there is enough sparsity, but sparsity isn't testable. So we have to use it with a lot of caution. So what do we do if we are not willing to do this sparsity assumption, to work under this sparsity assumption? Even if we were willing to say, well, these assumptions are true, we can get consistent estimates of the CAT and valid inference. Even then, you have to start. When you go in practice to implement the machine learning, it's a huge engineering effort, which is sometimes a little bit ahead of the theory as well. The justification for the test is heuristics and practice-based. So, are we sure enough in the causal validity of this estimate to take it to a policymaker? I think we are in the case of Lasso, which is if we have enough sparsity. But for all the other tools, there is so many decisions that have to be made that it seems to be a little bit dangerous to try and say, here is the full CAT. So what do we do here? Well, what we do is that we are going to be less ambitious. We will treat the machine learning tools as providing us just with predictor proxies for CAT, not the CAT. We are not going to assume that they are consistent and biased. And we will post-process the machine learning proxies to perform inference on very few features of CAT but features that a policymaker might be interested. And so our approach is generic because it can be used with any machine learning methods. And as before, we use double machine learning as the key tool. So it really works in two steps. The first step is to we split the sample, and in the auxiliary sample, we obtain the generic machine learning estimates of the baseline and the treatment effect, which we are calling the ML proxies, because we don't know if they are real or not. We can include any methods people like. We treat them as possibly biased and noisy predictor of the true baseline effect as well as CAT-A. And in the second step, we target a few key features of the conditional treatment effect, the best linear predictor of the CAT-A, group average treatment effect sorted by groups, for example, quintile of treatment effect, and a classification analysis that tells us the average characteristic of the unit in the most of least and least affected groups. Note that there will be careful in reading too much into the classification analysis, because again, there are many variables we could compare, so it's descriptive, not structural, but it can be very useful for policymaking. So what we do in this paper is to show that this sample splitting procedure works. We do repeated sample splitting and averages, and then we get the confidence interval out of this process as well. What do we find in this instance? So this is the effect of the pooled policy that we've estimated to be the best on average, that combines incentives, ambassadors, and SMS. What do we find? We find that for the least affected group, the treatment effects are in fact negative, whereas for the most affected group, the treatment effects are positive and large, 10 on average. We have very similar results for using neural net or elastic net, for example, with the other methods as well. So we're finding a huge heterogeneity in the treatment effect, which is important because you can see in blue the average treatment effect is basically not very meaningful except for the median group. Then we can look at so these are the effect for the most affected group and the least affected group. So the least affected group has a negative treatment effect, and the most affected group has a positive treatment effect. Now, let's discuss this result. Is it possible to have an increase of 300% of immunization? It's not crazy, because, for example, in the immunization project that I ran several years ago, we had an increase in immunization rate from 16% to 38%, so same order of magnitude. For the least affected group, there is a decrease in immunization. Is that plausible? Well, the incentives are very small. And there is a literature in economics that shows, and psychology, that shows that small incentive can decrease intrinsic motivation. Maybe it takes away the trust in immunization because people might be wondering why the government needs to pay them to do this. So that's an important result that needs to be discussed more. Now, for policy purpose, not only we need to tell people, the government, that there is heterogeneity, but we need to tell them what predicts it. And what is very interesting is that, in general, what predicts it is the previous status of immunization. So you might think that's totally obvious, that the effect would be larger in low immunization villages, but it's nothing mechanical. It could totally have been the opposite. But what we're finding here is that places where the treatment effects are smallest are the one where the largest fraction of kids were already immunized before the experiment. And places where the treatment effects are larger as the places where immunization level were lowest at baseline. So the policy recommendation is to implement the cheap intervention everywhere, but to prioritize the villages with very low immunization for the implementation of a package that includes incentives. What's interesting is that once you add the heterogeneity, you're finding that the policy, for the places that are the most affected, which are the group 5 here, even this policy is cost effective compared to the status quo. So if you add incentives, you actually don't lose money compared to doing nothing for each shot. Why is that the case? Well, it's because the level are sufficiently low and the increase are sufficiently large that your cost is more than offset by the fact that you're using your infrastructure, which is a fixed cost, in a more efficient way. So to conclude, machine learning has tremendous power to help us learn many useful and important things about the world. Not just about the world as defined by the data that we can easily get hold of, like commercial data sets such as e-commerce, fantasy leagues, photos of people, etc., or even language, but also data sets that needs to be acquired, that needs to be hunted in the real world, and that have implications that are extraordinarily important for the health and well-being of a large number of people. But for this, it's important to not let your questions be defined by what data is easily accessible and what questions are of immediate use to industry. There is tremendous value in talking to practitioners in many fields who may have questions and data for you and puzzles. From my collaboration with my economics colleague has been extremely productive and enjoyable for me, obviously, but I also think it has been productive for them in terms of generating important questions that have kept them busy. To finish, I have a few kind of a wish list for things that could be developed. First, the machine learning tools are very data greedy. I think you're used to work with a big data set, and they are often, therefore, impractical outside of a large applications where data sets is generated in very large quantity. So I would love to have machine learning tools for smaller data sets. I would also love to have machine learning tools for data cleaning, anonymizing, consistency check, and such things. It might not look very sexy or fancy to do that, but you have to realize that there is a huge trove of administrative data that you can find in developing countries. They are increasingly available and available to researchers. And they combine, the scale. If you look at the scale of a country like India, for example, it's millions and millions and millions of people. There is more and more interest from the point of view of the government to share this data with researchers, but the data is a mess. And finding ways systematic ways to clean it and make it available would actually be of tremendous value so that a lot of people can use it to do useful things. Finally, I would love to have a good ML tools for multiple inference for many outcomes. Here I worked only with one outcome, which does not just blindly penalize for running many regressions. So I'm sure many of you are already working on that. But if you, and I'm not yet aware, but if you are not, that is like a little summer project if you're interested. Thank you very much for inviting me. Again, I'm so delighted to have this chance to interact with you. And I look forward to many years of continuing to push this agenda with my question and my naivete and my interest. And I thank you for deploying your intelligence, your skills, and your tools for this important problem. Bye-bye.
Okay, so thank you very much, Esther, for this inspiring talk. I think there are many questions, and I have also many to ask. For now, we are going to look at these questions. So maybe there is a general question here about can the generic machine learning approach also be used with observational data or only with randomized control trials? Okay, I think this question might be understood in the sense that are you only focusing on randomized control trials, or are you also play around